let's talk about gradient descent and subgradient descent. Gradient descent. So we want to minimize f, and so a good way is to approximate it by a linear function. So we approximate it by a linear function, which is f of x at x naught plus gradient of f of x and multiplied by times x minus x naught. You see, if f is a linear function like this, then you just go and roll down. So it's so easy. You understand how to minimize the function. But what if your function is nonlinear? So at point x null, you have a linear approximation of that. So a good approximation. And so our goal is to find the minimization of this linear approximation, which is f of xt plus inner product of gradient of f xt times x minus xt. This is the linear approximation, plus you try to add a quadratic term like this to eta x minus xt squared, and this term is for penalizing x. So we use this quadratic term to penalize because you don't want to go too far from x. That's why you don't want to go too far from xt. That's why we add this extra quadratic term, And so you take the derivative, and set to 0 as usual. You see, the derivative of this one with respect to x is 0 plus the derivative of the second term with respect to 0 with respect to x is gradient of x at xt, and the third term, which is the penalizing quadratic term, is when you take derivative, it becomes 1 over eta times x minus xt, and you set the derivative to 0. So what you get is just the gradient descent algorithm. Xt plus 1, I told you this is the arg mean of that, is equal to xt minus step size eta. This is eta that we use here, step size time gradient of f at point xt. So this is the gradient descent algorithm. So when this term, when this penalizing term is too high, it means that eta is too small, your step size is too small. So you don't want to go very far at all. And so this is the intuition behind gradient descent. I give you a smooth example and a non-smooth example. So for the smooth example, the smooth function that I use, for example, is f of x is equal to this one. So you use the gradient descent. So x plus is equal to x minus eta gradient of f, which is 6x plus 4, and this is your gradient step. For the non-smooth example, I use the popular example of f of x is equal to x. And you see, again, we can use the gradient descent, But we call it gradient subgradient descent, because here at point 0 it is not differentiable, it is non-smooth at 0. So xt minus eta g xt, where g is inside your subdifferential of f. And so if xt is less than 0, you get xt plus 1, xt plus eta. If xt is less than 0, is greater than 0 now, then xt plus 1 is equal to xt minus eta. So every step moves us closer by eta when xt is greater than eta. But when xt is less than eta, you cannot improve. So when you are too far, yes, you can improve, but here you have an overshoot and you cannot improve. So you keep overshooting. And another example, which is from R2, x1 and x2, is 10x1 plus x2. So the shape of the contours are like this, one, and these are the contours of this function. For example, at point 0 and -3, at x equal to -3, we have a non-smooth point. So this is a subgradient, and you know that f of x minus eta gx is sometimes now greater than fx, unlike the smooth example that in each step you get closer, so it's a real descent algorithm, not just a name. But in subgradient algorithm, when you have a non-smooth function, then sometimes you get bad luck, and even you increase the function, which we don't want because we want to minimize that. So what we realize and we conclude is that gradient descent improves at every iteration, unlike subgradient. And the second point, that gradient descent can take big step size. When you're too far away, you can get big step size and you get good result. You get closer to the optimal solution, and we call this property self-tuning property. But we don't see that for non-smooth version. So, and the third point is that the gradient descent algorithm takes bigger steps when far away